started. Okay, last lecture we all had a couple of questions, right? The thing is, each of those techniques, you will again learn them as a separate lecture. Okay, the idea behind those questions was to make sure you guys are prepared. And of course, each of those lectures in future, they will also explain the technique in detail. Sometimes students don't get it in the beginning. So that's why I did this where I grouped all the principles in one lecture. Okay, today we are going to learn a bit about surface energy, surface charge and surface potential. We'll go one by one what each of these terms mean. Now, surface charge. The origin of surface charges can be some groups that are initially uncharged, but then at the right condition, at the right pH, they become charged. For example, here you have a amine group. How many of you know the term isoelectric pH? Raise your hands. Isoelectric point. No. Okay. Isoelectric point is the pH at which either molecules get ionized or it's the other way around. For example, if you have, let's say glucuronic acid. That's right. And this proton, it can be lost to give. I'm not drawing this part of the molecule. Okay. Let's say I'll call this Gu. GuCOO minus plus H plus. This dissociation happens only above a certain pH, okay, and that's isoelectric pH. The pH above which the dissociation happens, that's isoelectric pH. Even the other way around is true. If you go below isoelectric pH, carboxylate anion will become carboxylic acid. Okay, so it doesn't have any charge. Like that, if you have a molecule, some molecule that has an amino group, NH2, here there was a proton lost. The amine group is capable of taking up a proton to become NH3 plus. Okay, and so now it's going from uncharged to positive. And this pH at which this happens is also called isoelectric pH. So different groups have different isoelectric pH. So now, for example, I'm showing a surface which is not charged. Let's say you have pH below isoelectric pH. Higher pH means higher hydroxyl ion concentration, right? So you have more protonation, and that's why you have a positive charge developing on the surface. The opposite here is here, where the pH should be greater than isoelectric pH because it is deprotonation. Okay, you're losing your proton here to get a negative charge. Okay. Now these are two examples where we can have charges developing because of loss or gain of proton. There are other groups, for example, sulfate group, phosphate group. They also lose proton to give a negative charge. Okay, the other mechanism how surfaces gain charge is by selective absorption. For example, if you take a surface that is made of silver iodide, this material, this crystal has the property that it selectively absorbs silver ions. So once the absorption is over, it gains a positive charge. In the case of gold metal, it has the property of absorbing chloride ions, so the surface will gain a negative charge. So these are the two most common mechanisms how the surface becomes charged. Now, why is it important to study charges on surfaces? Now, if you take the colloidal chemistry, we have the stability of colloids depending on a lot of properties which can lead it to flotation, it can lead to flocculation, and then it can lead to coalescence where particles join to become bigger particles, and then sedimentation. And for different applications we need the colloids to behave differently. And the reason one of the main reasons why colloids behave the way they behave is because of surface charge. One main mechanism how you can keep them apart, not to interact with each other, to undergo any of these interactions, is to surround them with charges, because like charges repel each other, they will stay away from each other. Okay? So this is electrostatic repulsion. We can also have polymers that physically hinder two particles from coming close to each other, and that's called steric stabilization. And now we will focus mainly on the charge part for this lecture. Now we'll understand what is the relationship between surface charge and surface potential. Before I go to this slide, are there any questions? I can see a lot of faces, a lot of question marks. Surface charge, is that clear? How surfaces get charged, is that clear, or should I explain again? Okay, I'll continue. Okay, you guys can stop me anytime. Okay. Okay, as I told before, there are various mechanisms how charge is developed on a surface. Okay. We learned in our previous lectures that charge produces electric field. The way we define surface potential is when you bring a unit positive charge. Let's say you want to define what is potential at point A due to the charge on this surface. Now you bring a unit charge from infinity to this point. Depending on the charge here, you have to either spend energy or you will get energy. Okay? And the energy spent in bringing a unit positive charge from infinity to a point A is defined as the potential at point A. It's the energy that you need to give or take to bring a unit charge to that point. And the whole reason behind electric potential is because you have surface charges that produce electric field, and charges experience force in electric field. Okay? So now you have surface charge density, which is defined as number of charges per unit area, and these charges produce electric field, and that is a source of electric potential. Okay, so now okay, there's one more point on this. If, like I said, you either spend energy or you lose energy, you have to work against the field or you're working with the field. Depending on that, you can define what is the potential. If it is negative, that means you are doing negative work. What do you mean by negative work is you're working with the field. You actually gain energy. It's like pushing a magnet towards another magnet that is pulling it. Okay, you're not actually pushing. You're going with the magnet. You're just leading. You're just giving way. But then on the other hand, the potential is positive. The potential is negative if you have to push against the field. Okay, if there is one magnet that is repelling another magnet and you're forcing it closer, okay, that you're doing positive work. The negative work is when you're working with the field. Okay, you can think about this later. It's a bit it needs a bit of thinking. Okay, reflection. Now, one effect of surface potential around a charge is the following. If you take a particle in a solution in water, let's say it's anionic particle, okay, and you have a lot of positive and negative ions. Let's say it's an electrolyte solution. Now, because it has potential, it attracts the ions of the right charge, it repels the negative charges. Okay, so now after equilibrium, you will find this distribution where the negative charges have attracted the positive charges in the medium, so the positive charges are closer to the particle, and the negative charges are kind of repelled apart. Okay, so now this is the concept of double layer, electrical double layer. So this is a very simplified representation. I will go into a more detailed one. Before we go into that, I will give a realistic picture of what is actually surface charge. Okay, so now you have a surface. In the first slide, I mentioned there are various mechanisms how ions absorb or ions dissociate to give charge. Those ions that give rise to charge, they don't have solvation. They are not surrounded by solvent. They are just bare ions, and those are called. Okay, I'll tell in the next slide what they are called. Now, if you take a cation or an anion in solution, they're not always just alone. They're always surrounded by solvent molecules, and this is called solvation. And you always have cation or anion surrounded by, for example, here what I'm showing is these two green spheres. They are hydrogens, and this is the oxygen. Oxygen has a dipole moment which is partially negative, and these two hydrogens have partial positive. So now if you see around a cation, the oxygen is pointing to the cation, okay, because the oxygen is slightly negatively charged, okay. And here it's the opposite, it's the hydrogens that are pointing. So now depending on the anion cation, the number of solvent molecules surrounding each ion changes, the orientation of solvent molecules changes. Now if you take a negatively charged surface, okay, and dip it in a solution that has negative and positive ions, now we have the first layer of ions that are actually bound to the surface. These are not, the distinction between these ions and this ion is that this is not bound to the surface because of electrostatic attraction. They are bound due to, let's say, acid-base interaction or van der Waals interaction, okay. But then the reason why these cations are here is because the negative is attracting positive. This is electrostatic. This is one main distinction between the ions that contribute to the charge and the ones that form the electrostatically attracted ion. Okay. So now the first layer is compact non-solvated ions. They are non-Coulombic. Coulombic is electrostatic. It's another way of expressing positive negative attraction. Okay. And this is a charge contributing layer. This is layer 1. And you have layer 2, which consists of ions that try to neutralize this charge because of the potential generated by this charge. So now if you see, you have layer 1, layer 2, and that's why it's called double layer model. Now within the double layer, you can further classify them into more layers. Okay. Now we will go in more detail in this layer. Now we can draw an imaginary line in the counter ion layer. Let's say we call this whole thing the second layer, the layer 2. That's the counter ion layer. You can have two types of ions. Now there is an imaginary blue line here. Okay. Below that line, these ions will not be able to diffuse around freely. They are stuck. But then these ions, they are able to move around. Okay. And that's why this layer is called the diffuse layer, because the ions are able to diffuse around. Here the ions are stuck, and that's why it's called the Stern layer. Okay, so now the same diagram, but then we have the potential determining layer, which is the compact layer. And now when, let's say you imagine that this particle is moving in a solution. Okay, now the question is, how much of liquid travels through and how much of liquid travels with the particle. Okay, I'll draw something to make it easier. So now if you take a particle, okay, now there is liquid everywhere. Now when the particle moves, where is the boundary where the liquid is left behind and only the particle is moving? There will always be some addition between the liquid and the particle, and as you move up, the addition decreases. Okay, so now when it moves forward, there will be a thin layer of liquid that actually moves with the particle. Okay, can you guys imagine that? Right? It's the way to imagine that is, let's say this layer of water is stuck to the surface, and the remaining water, the molecules here, they are not that strongly bound, so they just slip back when the particle moves forward. Okay, that's what is called the shear or slipping plane, where if this is the particle, this is the boundary. When the particle is moving forward or backward, the solvent molecules below here, below this line, they travel with the particle. The solvent molecules above this line, they slip away. Okay, that's why it's called the slipping plane or the shear plane. Now, the reason why this slipping plane is very important is because when you measure the potential of a particle, actually if you imagine the negative charge is something here, let's say x. Now the positive charges, they attenuate the electric field, okay, they cancel out the electric field. So as the electric field reaches this point, it keeps decreasing because there are positive charges. They cancel more and more as you move here. And when the particle is moving, a moving particle's potential that you see outside, that is the potential that you see here. And that's why when you measure potential of particles that are moving in solution, which is always the case, you don't have any particles static in solution, they always are moving. So when you measure potential, you're not actually measuring this potential, you're measuring the potential which is in this region. Okay, that's why it's important to understand what is slipping plane, and this potential is called zeta potential. Now this is the graph which shows variation of potential as a function of distance. So now here, let's say this is the surface of the particle and you're moving away from the particle as a function of distance. Here you have the intensity of electric field. Okay, so now at the surface, okay, you have surface charge, which is the highest surface charge. So that's why you have psi naught, which is the surface potential itself. Okay, and the electric field potential will be highest at the surface. But as you move away from the surface, the potential keeps decreasing. Why is that? Because the electric field is attenuated by the counter cations, okay, as I told in the previous slide. So now, as you move down in the stern plane, where there are counter ions that are not diffusing, you have a linear variation. So from this point to this point, the potential drops linearly, and then from stern plane onwards, it drops exponentially. Okay. Now, the thing we need to note is there are two important parameters. One is zeta potential, which is the potential at the slipping plane, and the other thing is, this is a very theoretical concept. What I'm going to talk is theoretical value. This is called the Debye length, which is the distance over which the psi naught becomes 1 over E. Okay. So now, why is this so important? I will tell in a couple of slides what if the Debye length becomes very important when it comes to measuring surface potential. Okay. So now the conclusion from this slide is you have surface charge which is responsible for psi naught, but then for a given solvent which has given concentration of ions, what you measure at the slipping plane is the zeta potential. Okay. Okay, now let's look at some of the effects. So now you guys know what is slipping plane and you have idea about what is zeta potential. Now let's see some of the effects of surface charge when they are subjected to electric field, external electric field. Okay, so now let's say you take a solution of ions, okay, and you put it connected to an electrode, and then you connect, let's say, to a battery. Okay, so now the positive produces, the anode produces an electric field, and the cathode also produces corresponding field. So now the negative charges are attracted to the anode, the positive charges are attracted to the cathode. So there is a separation of ions. The ions move to the respective electrodes. This whole process is called electrophoresis. Okay. Now this is one of the electrokinetic phenomenon. Now there is the other possibility where there is electroosmosis, where in the presence of an external applied electric field, the solvent moves. As I mentioned before, if you take a surface that is negatively charged, okay, it attracts the counter ions, in this case the cations. When you apply external voltage, we know that, for example, the cations move to the cathode. The cations move to the cathode. As I told before, in the diffuse layer, you have ions that can diffuse, but then in the stern layer, there are ions that cannot diffuse. So now, when the ions move, they will take with them some of the solvent that was surrounding them. Okay, and so when you apply external voltage, it's not just the ions that will start moving. They will also carry some solvent, and that will cause a flow of solvent because of the applied electric field. So now, because there is movement of solvent, we call that osmosis. Okay? And because it's happening due to external applied field, it's called electroosmosis. Okay. Now let's go to the third phenomenon, which is called streaming current or streaming potential. Now this is the phenomenon that is opposite of electroosmosis. In electroosmosis, we applied electric field and solvent moved. Okay. Here, let's say you have a solution of ions, and the negative charges, they attract counter cations. When you apply a pressure across this channel, okay, you have a flow of liquid. What the flow does is it washes away all these counter cations. Okay, when the ions are gone, there is a net charge that is developed because of laws of electroneutrality. There is no neutral condition because of the counter cations being flown away by the flow of water. Okay, and this process is called streaming potential. The potential developed due to the water flowing, that's called streaming potential, and the ions that are actually being carried away, that can conduct some current, and that's called the streaming current. Now let's see how streaming current can be used to find the surface potential of a surface, and also let's go into how nanoparticle surface potential can be measured experimentally. Okay. So now we have nanoparticles that can be from 1 to thousands of nanometers. Now we are going to use the property of electrophoresis to get the idea of surface potential, okay, of nanoparticles. So first we'll go into this, and then later we'll use surface streaming potential to find surface potential of huge surfaces. Okay, now I'm going to talk a bit about scattering again, but it won't be that confusing as Raman. Now we are going to talk about Rayleigh scattering, where there is no exchange of energy between the incoming photon and the particle. Okay, so there is an incoming photon, it couples momentarily with the electric field of the matter, and then it is emitted back, scattered back. Emitted back is the wrong word. It's scattered back in all directions, and the key thing is the incoming light and the scattered light have exactly the same wavelength. Now this is assuming in all your slides with Raman spectroscopy, we all assume that this particle, the scattering particle, was static. What if the particle is moving with a velocity? That brings in an effect called Doppler effect. So now let's say this particle is emitting an electromagnetic wave with a frequency. Okay. So now if let's say you are here. Okay. Now if this particle that is emitting, if it is moving away from the source, this same wave, it gets a bit stretched. Okay. On the other hand, if the particle is moving closer to the observer, it gets a bit compressed. Okay. So now this is actually in terms of wavelength of light or frequency of light. This is change in frequency, right? When you squeeze it, the number of cycles per second is changing. That's actually change in frequency, if you remember what is light. Now let's apply that principle, Doppler effect, to a particle. Okay, so now you have a nanoparticle that is in solution. Let's say it's static. It has zero velocity. Okay, so now there is incoming light with frequency nu, and the scattered photon is emitted. It has the same frequency as the incident photon. Okay, but then if we have a condition where the particle is moving with a velocity greater than zero, what will happen now? Because if the observer is here, as you saw on the previous slide, the wave gets compressed. That means the frequency goes up. Okay, so now in the case where velocity is greater than zero, you have here this V stands for velocity, and the italicized V, that stands for frequency. Okay, that's called nu. The notation is here. Now, when the velocity is greater than 0 with respect to observer, the frequency goes up. So it's nu plus delta nu. Now, what about if the particle was moving away from the observer? Okay, what will happen? What do you think will happen? So in this case, if it is moving towards the observer, you have increase in frequency. It's the opposite, right? It's that simple. So you will have nu minus delta nu. It's the Doppler effect in the opposite direction. Okay. Here, moving away, it should be negative. Okay, that's wrong. That's a mistake there. Okay, now how do we get the information out? Now we know that a particle, when it is moving closer or away from the observer, you get Doppler effect. Now we are going to use the process, the phenomenon of interference to get this information out. How do we know by how much they are undergoing Doppler shift? Okay, and this I think we studied in the second lecture where I told you how interference happens, constructive and destructive interference. Now, what we do is we have the reference wavelength and we have the scattered wavelength, the reference light and the scattered light. Now we make them interfere with each other. Depending on how much they have shifted with respect to each other, they will undergo interference. And the resultant pattern is called the beat frequency. And this frequency of this beat is directly proportional to how much these guys differ from each other. Okay, and based on beat frequency, the phase difference between beat frequency and the reference wave frequency, you can tell whether it's positive Doppler shift or negative Doppler shift. Okay. Okay, the frequency of scattered light is directly linked to the velocity of particle. Now we are going to the actual technique, how we use electrophoresis to get the velocity of the particle. Okay. For this, we are going to use a property of particle called electrophoretic mobility. Okay. Electrophoretic mobility is, it can be defined as the increase in velocity of the particle with unit increase in the field strength or the voltage applied. Okay. So now you have a charged particle. We all know that when you apply external voltage, it moves to the anode or cathode depending on its charge. Now, the electrophoretic mobility is the increase in velocity per increase in the voltage. And the electrophoretic mobility is linked to the Doppler shift by this relationship. Okay. And here E is the potential applied. So all that you need to do is you need to apply a potential, measure the velocity, and you will get you apply a potential, you measure the Doppler shift, then you can get the electrophoretic mobility. Okay. Now, how electrophoretic mobility can be used to get electric potential, I will come to that in 2 slides. Okay. But this is first requirement in order to get the electric potential at the slipping plane. So now, this is the relationship between the electrophoretic mobility and zeta potential. If you remember, zeta potential is the potential measured at the slipping plane, okay, which is also linked to the surface potential at the charge. Now this is the actual setup. How we do it? It's based on scattering. Just like Raman spectroscopy, you have a source of laser, you have your sample with particles here. Now, the sample holder is such that it gives you the option of applying potential, and because of the potential, the mobility of the particles changes. Okay? The particles either accelerate towards the anode or the cathode depending on their charge. So now, depending on the Doppler shift which occurs, which you calculate using the scattering, you can calculate the velocity, and the velocity can be used to calculate the electrophoretic mobility, which is also a kind of velocity, can be used to calculate the zeta potential. Okay. Is this part clear? Should I go through this once again, or is this okay? Okay, I'll go through. I'll continue, okay? Okay, so this is a more detailed picture of what the cell looks like. You have a cell where there is a volume of solution that contains your particles. Here the particles are shown. You have the cathode and the anode. When you apply potential, what happens is the negatively charged particles, they start moving towards the positive, and the positively charged particles, they start moving towards the negative. Okay, and as soon as you apply voltage, the particles move with the velocity. Okay, now all that you need to do is, when you apply voltage, you need to study the scattered light, and then because of Doppler shift, you can guess whether the particles are moving in this direction towards the cathode or the anode, and depending on how fast they are moving, you can guess the zeta potential. So now, from the Doppler shift, you get the delta frequency. Okay, from that you get electrophoretic mobility, and then you plug in this equation, you get the zeta potential. Okay, here is an example. For example, if you have, let's say you had a particle which had no charge, zero zeta potential, its scattered frequency is the same. Okay, it doesn't get accelerated in the presence of electric field. Okay. On the other hand, if you have a positively charged particle, you can see that there is positive, the frequency has increased, the measured frequency of the scattered photon has increased. On the other hand, for the particle that has negative charge, it's the opposite. There's negative Doppler shift. Okay, so now we'll go back to the electrical double layer, because we want to study what is the effect of ionic strength on the zeta potential. Okay, so now let's say a condition where you have a surface with some solution, as we saw before, the potential drops linearly in the Stern layer, and then it drops exponentially. And this drop is because of the counter cations that are cancelling the electric field, as I mentioned before. Let's assume that you took this particle and then increased the electrolyte concentration, which means you have increased the number of anions and cations in the solution. Okay. So now what these ions are going to do is they're going to again accumulate here. Okay, because this region is where the counter cations accumulate. You have only selectively negative ions, assuming, let's say, this is a positively charged surface. Okay, so now because there is an increased number of ions in this region, what do you think will be the profile here? What do you think will be the rate at which the potential falls here? As I told before, this fall is due to the attenuation of electric field by counter cations. Okay, so now you're increasing the number of counter cations here. So what do you expect? What do you think will happen to the rate at which this falls? It will fall more rapidly, right? So now, if you increase the electrolyte concentration, the number of counter ions is increased. So the electric field will be attenuated even faster. So as a function of distance from the surface, the potential will drop at a much more rapid rate when compared to there was lower electrolyte. Okay? And now, what is the effect of that on the Debye length? Okay, Debye length was the length over which the surface potential became 1 over E. So that's E naught by E. Okay, so this is a theoretical value. Now, if you observe this, the red lines, they indicate the high electrolyte condition, and the green one, they indicate the low electrolyte condition. Okay, so now, because it was falling less rapidly, the green one, the Debye length is here. The epsilon naught, the psi naught, it attained a value of 1 over E at this distance. But then at high electrolyte concentration, because it's falling more rapidly, the 1 over E condition is reached even at a much closer distance to the surface. Okay, so Debye length is a kind of measure of how charge is getting dissipated. The electric field is getting dissipated as a function of distance. Okay, so now if you have a colloidal surface, two particles, if you remember my third slide where we studied the importance of colloidal stability, how it depends on surface charge. Okay, so now if you have two particles, okay, if you have two particles near each other, okay, now if you have low electrolyte concentrations and you have a situation where you have two particles that are at high electrolyte concentration, now let's say here the distance is 1 micrometer. Now because in this case, because in the low electrolyte concentration the Debye length is higher, okay, so now let's say in this case also the distance is 1 micrometer, let's say. Now the negative charges, they are repelling, okay, at 1 micron distance. Because the Debye length is higher, still this particle pair will experience higher repulsion, electrostatic repulsion, okay, because the charge, the electric potential is getting dissipated at a much lower pace in the case of low electrolyte. But on the other hand, if you take two particles, okay, now in high electrolyte concentration the dissipation is much more rapid, okay, so at this distance the distance is the same but they will experience lower electrostatic repulsion, okay. So this is one reason why it's very important to know the electrolyte concentration when you're measuring surface charges. And it is one way to, theoretical way to measure how surface charges are affecting surface potential is by calculating the Debye length. Okay, this is the formula for Debye length, okay. As I told, the higher the concentration of ions, the lower is the Debye length, inverse relationship. So that's what I'm showing here. The I stands for ionic strength. So you have inverse relationship. Now, why am I stressing so much on ionic strength and zeta potential? The reason is, if you're doing measurements in your lab where you take two surfaces, you're comparing charges of two surfaces, potentials of two surfaces. The thing is, you should be absolutely sure that the ionic strengths of both are the same. You cannot compare surface potential of one surface that is in 1 millimolar sodium chloride with another surface potential which is in pure water. It doesn't make sense to compare these two. Okay, you have to make sure the ionic strengths are the same. Okay, so now there's one more point that I mentioned in the first slide, the isoelectric pH. Now we'll come back to that. The effect of pH on zeta potential. Okay, the basic concept here is zeta potential is directly related to the surface charge. There is no surface charge, then you won't have any zeta potential. It's that simple. So now, if you take an amine coated surface, okay, and if the pH range is 9 to 14, okay, it's above the isoelectric pH. So there is no protonation, so they are neutral. But if you take the pH in this range, pH below isoelectric pH, then the amino groups get protonated. Okay, they get a positive charge. Now, if you measure zeta potential of these particles are the same. Okay, they are the same particle, but then all that you have changed is the pH. So if you measure zeta potential of this particle, you will get a positive zeta potential. Okay, but then if you measure zeta potential of this particle in the pH 9 to 14, you won't get any zeta potential. Okay, the same applies to this particle where we have carboxyl coated surface. Okay, now in the pH range 0 to 4, the carboxyl groups are protonated. There is no negative charge. So if you take the pH above the isoelectric pH, which is, let's say, 4, in this range you will have deprotonation happening. Okay, which means the surface will be negatively charged. Okay, now I want you all to think about this. Okay, you guys are not going to answer. I have already guessed that today you guys are not talking much. Let's say you have now I told two surfaces where it's carboxyl or it's amino. Let's take a surface that has both. Okay, let's mix them together. Now, just think about this. Okay, let's say what will happen if you have pH 2. Just think about it. Okay, think about it. So pH 2, okay, now pH 2 for amino group, it falls in this range, so it's positive, right? And in the case of carboxyl, it falls in this range, so there is no negative charge. So if you take a surface that has both amino and carboxyl groups and dip it in water, let's say, which has pH 2, what all the carboxyl groups remain uncharged, but the amino groups, they become protonated. So the zeta potential, if you measure the zeta potential of this particle, it will be positive, right? Yeah. Okay, now once again, okay, let's go through this again. So now you have pH 6, okay, pH 6. So what, just place this pH 6, place this in both these situations in the range there where it belongs. Okay, pH 6, it belongs in this range for amino group, so that's protonated. pH 6 belongs to this range in the case of anionic. So it will have both positive and negative. Okay, now the question is, so what charge will the surface have? What zeta potential will it have? They are both positive and negative charges. So if you measure zeta potential, what will you observe? No. It depends on how many of these groups are there. So now, because both are charged, so if it will be positive or negative depending on relative amount of these. Okay, you understand that? If there are more, let's say if there are 4 negative charges and only 3 positive charges.
But 6 is too high for NH3.
6. Yes, 6 is here in between. No, it's like this, okay? So they cancel each other. Let's say a positive and negative, they cancel each other. It's mathematics. And the M, the overall charge of the surface, it depends on what is the net charge. Okay? So now if you have both carboxyl and amino, all that you need to do is calculate total number of amino minus total number of carboxyl. If that value, the net value is positive, then this particle will be positively charged, and if it is the other way around, it will be negatively charged. And there are molecules that have exactly equal number of positive and negative charges. Okay, so when you apply electric field to that kind of molecule, it doesn't move to either anode or cathode, even though the particle is charged. And those kind of molecules, they are called sweeter ionic molecules. It's nothing to do with this, but I'm just telling you for the information. Okay, so that you heard the word. Okay, 11. I'll go through this faster. Okay, I know I'm boring you guys. Okay, 11. You will place it here. Okay, there is no amino group charge coming from amino group, and you have negative charges coming from carboxyl group. So you will get a negative zeta potential. Okay. Okay. So now, how we have dealt with nanoparticles. Was it clear? The nanoparticles surface potential, was it clear? Should we continue, or you guys have some doubt? I know that it's a bit tricky concept. We can, if you have any doubts, you can ask me now. Okay, I'll continue. Okay, I'll continue. Okay, so now we are going to deal with huge surfaces. Okay, and for that we use a concept called streaming potential. As I mentioned before, streaming potential is the potential developed when, as a consequence of water solvent carrying away the countercations from the surface above the slipping plane. So now you take a negatively charged surface, it attracts the countercations, okay, and the slipping or the shear plane is where the solvent doesn't move above the solvent, above the shear plane, the solvent just slips away. So now when you apply a solvent flow, you have these ions flown away. Now before, this whole entity was electrically neutral. Okay, there was a bunch of negative charges and the positive charges came and neutralized it. Because they are gone, there is an imbalance in electrical charge now. Electrical charge produces potential, right? That's a given. So now imbalance in electrical charge that produces a potential. Now, because the flow is in this direction, the cations will be accumulated here. The surface will be more negatively charged here and more positively charged here. That's why we get a potential, negative potential here and a positive potential here. The polarity reason is based on the flow direction. Okay, so now let's say this is the setup for how we measure the zeta potential using streaming potential or current. Okay, so now you take a surface that is negatively charged and there are counter cations, and this green line, that's the slipping plane. Okay, so now you let's say you apply pressure where the applied pressure causes water to flow from here, here and then back. Okay, now because of this flow, you have the counter cations being moved in this direction. Okay, because ions are moving, ions can also conduct current, not just electrons. Okay, so because ions are moving in one direction, that constitutes a current. Charges are moving in one direction, and that is called the streaming current. And because the ions are gone, there is imbalance in electrical neutrality, and that generates a potential, and that's called the streaming potential. Now, because of this potential, what happens is that these ions inside the shear plane, they start moving in the direction towards the negative. Okay, because here these ions can't move because the water is opposing them. Okay, because of the potential, you have the counter cations inside the slipping plane, below the slipping plane, they start moving. Okay, and this constitutes the conduction current. Okay, we can measure both the streaming potential and the streaming current if you apply a voltmeter or a amperometer across this channel. That's all you need to do. So you can measure, and depending on the flow, depending on the surface charge, the current generated will be varied. The potential developed also will be varied. So now this is one more setup where instead of making a channel, okay, what you can do is you can have a rod and you attach the surface below this rod, and the rod rotates. Okay, because of the rotation, there's a shear generated that causes the flow of water in this fashion. Okay, because of this flow, now this is a negatively charged surface. Now you have the counter cations. Because of the flow, the counter cations are taken away from the surface, and that generates a potential. So now all that you need to do is put an electrode here, and measure the potential, and you can get the zeta potential of the surface. Now I told you the setup, how to measure, how to generate the pressure difference and then cause the streaming potential. These are the formulas relating zeta potential, the pressure difference and the voltage measured. Okay, so now we have a relationship between zeta potential and the pressure difference and the voltage. And the previous both slides, there are two different setups how you can measure the streaming potential. So now we have a solution how to measure zeta potential of a nanoparticle, also of a surface. Now, how do we distinguish? Let's say surface potential is useful. It is also useful to get the idea about surface charge. It's very tricky to get surface charge. To get a complete idea of surface charge is very tricky. I'll tell you why. For example, these are two simple ways by which you can measure charges. For example, here you do titrations. For example, you have a negative charge and you titrate it against a cationic polymer. Okay, depending on the surface charge, you'll have the consumption of cation. You can do a conductometric titration. We have studied about this before in the second lecture. In the first lecture. In the first lecture we studied conductometric titration. Okay, and then the other reaction that we are depending on is acid-base reaction, where let's say a carboxyl reacts with sodium hydroxide to become sodium carboxylate. and this reaction is stoichiometric, so you can follow using conductometric titration again or pH titration. The problem with these both techniques, you can't relate. For example, let's say you're titrating carboxyls. What if there are sulfate groups? What if there are phosphate groups? So you're just assuming that all the negative charges from your surface is coming from carboxyl. That's your assumption. Okay. So the risk of taking this as the surface charge is based on a big approximation that your surface has charges that completely undergo this reaction. Okay, so this is one drawback of using titrations to get surface charge. There might be charges that are not contributing to the titration. Okay, but this is very commonly accepted. It is accepted because the groups that are causing surface charge in plant-based material, they are very well known. So you can be very sure that you have caused all the groups to go through this titration reaction. Okay, so I would say in the case of unknown samples, titration is a bit complicated. But if you know the origin of sample and if you are absolutely sure all the ranges of anionic cationic charges that are available in the surface, then titration becomes a very good technique to understand what is the surface charge density. Okay, so now I will give one example. I've overshot. Okay, this maybe 4 or 5 slides and then we take a break. Okay. I'll give an example where we have cellulose nanocrystal. Okay, and let's say we're cationizing we are making it cationic by introducing the quaternary ammonium nitrogen. So now here is an example where they experimentally measure the zeta potential. Okay, so now the starting material, it has negative charge because of the sulfate groups. Okay, after they added the cationic charges, the zeta potential has become positive. That's because of these positive groups. Okay, so now when you do a surface reaction, surface modification where you go from anionic to cationic, you can follow that using zeta potential. And surface charge density is another parameter where we can measure the number of, let's say in this case, they measure the number of sulfate groups on the surface per nanometer square. And here in this sample, they measure the number of chloride groups. Okay? Even this gives a measure of how much of this reaction is happening. So these are two examples where we get idea about surface charge and surface potential, which can be applied to characterize particles. This is a nanoparticle for your information. Okay, so the number of anionic groups is higher than the cationic groups. That's a very important information. It can be useful when it comes to using this material for some colloidal applications. Okay, so now, okay, that's the end of it. We first started with the origin of surface charges, and then we saw how surface charge is very important to colloidal stability, and the relationship between surface charge and surface potential. This is one key thing you guys need to distinguish between surface charge and surface potential, and which techniques give you surface charge, which techniques give you surface potential. Okay, you have to distinguish between these two very clearly. Okay, and then we went to the electrical double layer, and the main concept in electrical double layer is the slipping plane or the shear plane, and the types of electrokinetic phenomena where we studied electrophoresis, electroosmosis, and streaming potential and current. And we studied how electrophoresis can be the basis of calculating the zeta potential of nanoparticles. We used Doppler effect for that, and then we came to use streaming potential or current to measure the potential of a surface, and then surface charge density that can be calculated using titrations. And then we saw one example where surface charge and surface potential was used to characterize a reaction. Okay, we'll take a 5 minutes break.